Hey, what's up, SUPA classes? We're going to continue on with our notes, and we're going to get into molecular shapes. And eventually we'll get into some VSEPR stuff. So let's see, where to start. So our Lewis structures, or our dot diagrams, will give us a general bonding and general structure of a molecule. We're going to use these Lewis structures to produce structural models. We will use Lewis structures to construct and draw structural models, or structural, this pen's dying. Draw structural models of molecules. Okay, I want to stress that you have to start with the dot diagram before you can draw these structural models. Okay, so let's say we want to draw, I don't know, methane, CH4. All right, so the first thing you need to do is we need to know what these bonds look like. All right, so when we draw the dot diagram, we get something like this. Now, this is the dot diagram. Okay, it doesn't have any dashes yet. Okay, it doesn't have any dashes. Okay, so this is our Lewis structure. Now, once we have this Lewis structure drawn, now we can draw the structural formula. Okay, if it's a single bond, we use a dash. If it's a double bond, we use double dash. Finally, that would be our triple. So this is my single, double, triple. Right, now, so these are all single bonds. Now, we're going to learn this. This is a tetrahedral shape, and carbon would go in the middle. Right? And our structural formulas try to show some shape. Right? So in this case, we would draw something like this, and that's a dotted line. Right? So this would be our structural model of methane. Right? But to get to here, you have to start with this guy, because you need to know what type of bonds there are. So let's talk about our central atom. Okay, so we're going to always look at this central atom. That's our focus. Okay, so we always look at the central atom and count the atoms bonded to it. We use a general formula to describe these. And that general formula is capital A, capital B, small n. All right, so A represents our central atom. B represents the bonded atoms. and the N represents the number of those bonded atoms. So if we were to come back here and look at our methane, carbon is our central atom, right? And it has 1, 2, 3, 4 hydrogens off of it. So this one would be an AB4 molecule. Okay, so here, we don't use this is just a general formula for the different types of molecules that we have. All right, so this is saying we have a central molecule and there are 4 bonded atoms coming off of it. So we'll use this notation as we go through some of these things. So the first thing I want to start with, let's number these 1. If there are only 2 atoms bonded together, it's going to be a linear molecule. It's the only thing it can be. So for example, let's say we look at H2, and here it is. Here's our diatomic hydrogen. We start with our dot diagram. It has 1 pair of electrons between it. So our structural formula would look like this. Okay. This is a linear shape. Okay, so if you only have 2 atoms, they can only be lined up next to each other. Right? All right, so now let's start with our molecules that have a general formula of A, B, 2. Okay, so we have a central atom and we have 2 bonded molecules to atoms to it. And we can have 2 types. We can have a linear and we can have bent. So an example of an AB2 linear molecule would be something like this. Again, they're all lined up in a row, so it's linear, right? And this example is carbon dioxide. So CO2 is a linear molecule. Now the most famous bent molecule, ooh, and I don't have it built. Huh. Here it is. Who's that guy? So this is also an AB2. Here's my central atom. And it's got 2 bonded atoms off of it. Right, so this is H2O. And it's got this bent shape. And there's a reason for that, and we're going to talk about it. So those are the 2 shapes that our AB2 molecules take. Now we're going to talk about AB3 molecules. And they can take 3 shapes. We can have something called trigonal planar. We can have trigonal pyramidal. And we can have T-shaped. So the first example of a trigonal planar I want to use is SO3. And in this molecule, we're going to have sulfur in the middle. There's an oxygen coming here, an oxygen that's double bonded, and an oxygen here. And it forms this trigonal planar. And they're all in the same plane. And here it is. Okay, so this would represent my sulfur. Here's my oxygen, oxygen, and here's my double bonded oxygen. Now, this has actually got an equivalence form, right? And it shows resonance. Okay, so in reality, we don't see two singles and a double. We see something in between all of them. And we've talked about that before. But this is that trigonal planar. So they're all of the bonded atoms are in the same plane, okay, as the sulfur. Right? So this is what's called a trigonal planar shape. Our trigonal pyramidal ammonia is the one that we tend to use. Okay, there are others. When we draw a trigonal planar, we draw it like this. Okay, and this is a dotted line, and that means the hydrogen's either coming out or going into it. And here's an example of trigonal planar, trigonal pyramidal. All right, so if we compare it, we have them both on here. Okay, so this one, the three legs are coming off the same, all in the same plane. But in this one, they're being forced down, and there's a reason for that, and we're going to talk about that eventually. But when you get this shape, this is called a trigonal pyramidal. And then finally, we can have T-shaped. An example of a T-shaped would be ClF3. And it would look something like this. And this is T-shaped. This would be my chlorine and my 3 fluorines. Right? And notice that the T-shape is, again, all in the same plane. And there's a reason for that. And we'll talk more about that later. Right? But these are all in the same plane. And this is called T-shaped. So these are our AB3 molecules. AB4 molecules we've already talked about. Okay, and the only AB4 molecule that we have is a tetrahedral. Okay. Carbons love tetrahedral, so this is the typical one that we use is ammonia. Or not ammonia, methane, excuse me. And here's my tetrahedral. And it's got 4 legs. And that's the tetrahedral shape. So here's my central atom, my carbon, and my 4 hydrogens. Okay, and we try to show this shape. We put the carbon in the middle. Right? And if you look at this, these 3 hydrogens down here are all in the same plane. So we draw it this way, and this way. And then this guy right here is coming out towards you. So we use a dotted line to represent that H. Okay, so it can either mean that it's coming out towards you or it's going into the paper away from you. So that's our tetrahedral shape. And that's the only AB4 type of molecule. We were numbering, so this was 4 and this is 5. So these with AB5 molecules, these are going to be trigonal planar. Oh no, I lied. Trigonal bipyramidal. And do I have that built? I don't. Hold on, I'll build it for you. So this would look like, this isn't perfect, but it works okay. Okay, this is what it would look like. Now this technically is not quite right because I don't have the right holes, but that's okay. We can see what it's doing. All right, so our trigonal bipyramidal, it's got straight up and down, and then we have this 3 on the outside, just like this. Okay, and this would be actually a 120-degree angle here. So I could turn it like this for you. It'll look something like that. And an example of this would be PCl5. Now, as soon as you get over tetrahedrals, structural formulas are hard to show shape. All right, so here's my P, and we're going to draw my Cl coming up and my Cl coming down. All right, now this is the hard part. All right, so you can't really. So what we kind of do is we say that this one's in the plane, and then this one comes down here like this, and then this one comes up here like this. So these are my top and bottom ones, and then these are my 3 around it. Okay, so this is my AB5 molecule. There are other ones that we're going to talk about also, but we're just not quite ready. When we get into the next thing, we will talk about that in a minute. And the last one we're going to talk about are AB6 molecules. And these are our octahedrals. Perfect example is SF6. Right, this is where we have sulfur in the middle. We're going to have a fluorine coming up, a fluorine coming down. And then at 90-degree angles, and it's really just impossible to draw. This is how we draw it. We have the fluorines in a plane around it. Okay, so let me see if I can, sorry. Let me make it for you. So this would be our octahedral. And I'll put it like this. So if we look at it kind of like this, here's my sulfur. I have a fluorine coming down, a fluorine coming up. And then in the same plane, within a 90-degree angle here, I have 4 more fluorines. Okay, so this is an example of an octahedral. Now, there are variations that we're going to talk about with our AB5 molecules and our AB6 molecules. Right? And that's when we start taking some of these bonds away and putting in some other, just some unpaired electrons. And that's what we're going to talk about with what's called VSEPR theory, which is where we're going next. We developed this model to help us come up with these different shapes. Okay, and this stands for valence shell, electron pair, repulsion model. Oops. Sorry. Valence shell electron pair repulsion model. VSEPR. And this model is used to predict shapes of molecules. So we have to define a couple things here. The first thing we have to define is an electron domain. So an electron domain is a region where we will likely find electrons. Okay, so an electron domain is where we're probably going to find electrons. Now, there are two types of electron domains. We have bonding domains or bonding pairs. So in bonding pairs of electrons, this is where we have a pair or pairs of electrons shared between two atoms. And then the second type of electron domain we have are called non-bonding pairs. Or lone pairs. And these are a pair of electrons found on one atom. In other words, they're not part of any bond. We have bonding pairs and non-bonding pairs. So let's look at an example, and you got to be able to count these. So let's look at ammonia. So if we look at ammonia, we want to find our domains. Okay, we need to count them. So there are actually four domains here. This is a domain, this is a domain, this is a domain, and this is a domain. Right? So this up top is what's called a non-bonding pair. This one, and this one would be bonding pairs. So we have a total of 4 electron domains. One of them is a bonding, and 3 of them, excuse me, 3 of them are bonding. 1 is non-bonding. Now, in VSEPR, single, double, and triple bonds all are considered to be one electron domain. Okay, and let me show you what I mean. So if we have carbon dioxide, all right, we're going to look at the central atom, okay, because that's what we're always looking at, is we always focus on the central atom. And it has two double bonds. This is a bonding domain, though. It's one bonding domain. Now, we have two pairs of electrons in there. That's okay. It's a double bond, but it's still just one bonding domain. Same thing over here. We have two pairs of electrons. We have a double bond, but this is one area of space around it, all right? So this is one bonding domain over here. So in this case, we have two electron domains, and both of them are bonding domains. Okay, so we'd have two bonding domains, and we'd have 0 non-bonding domains. Let's look at this. This would be ethine, all right? And we're going to focus on this central atom. In reality, there are two central atoms, okay? But they're both going to be the same, right? So when we look at this guy, this is still considered one bonding domain. This is also considered to be one bonding domain. Even though this is a single and this is a triple, this is one area of space where we're going to find bonded electrons. And this is one area of space where we're going to find bonded electrons. Right? So this also has two electron domains. And both of them would be bonding domains. So when we're talking about this, we're really counting those areas of space where we're finding electrons. It doesn't matter how many are in there, right? And we're going to need to use this in our model because that's what we use to figure out our shape. Now, the electrons in the domains are negative. They're all negative. So if the electrons in the domains are negative, that means the electron domains themselves are negative. So if all of these domains are negative, what happens if you put two things with the same charge next to each other? Well, they're going to repel, and these electron domains are going to repel each other. Okay, so these electron domains repel and want to be as far from each other as possible. So molecules will form shapes that decrease the repulsion as much as possible. Okay, so how do we actually use VSEPR? Okay, first thing you really need to do is you need to draw your Lewis structure. Next thing you're going to do is you're going to count the number of electron domains. Okay, now remember there are bonding and non-bonding domains. And then finally, we're going to determine the molecular geometry using the reference sheet. And there's lots. They look all different, all right? But this is an example of a VSEPR electron sheet. And what it does, all right, it gives us bonding domains and non-bonding domains, and actually it's cut off over here. Is it better on this side? Yeah. Okay, so it also gives us the total number of electron domains, right? And then it gives us the different shapes that it can take. It gives us a base model and then different things that can do, right? Well, I'll post something for this, but this is right out of the textbook, I believe. All right, so we're going to use this chart, and it's going to give us these different shapes of what it should be. Let's go ahead and try it. So let's start with ammonia, and we already know what shape that takes. So there's my Lewis structure. All right, and then here we have one non-bonding, and we have 3 bonding, for a total of 4. 4 bonding domains. Okay, now what shape would this take? All right, no matter if we come up with 1 bonding and 1 non-bonding and 3 bonding, it will always take the same shape. So what we do is we come over here and we find, okay, so this would be a total of 4 here. This is a total of 3. This is a total of 2. Okay, so first we find that we have 4 bonding domains, and then we come over here and we look for our corresponding numbers. So here we have 1 non-bonding and 3 bonding. Okay, and here's our example. So this would be a trigonal pyramidal shape. Now, let's talk about why that's happening. Why is it doing this? Why isn't it just trigonal planar? Why isn't it just like this? Okay. Well, there are 4 domains that are all interacting with each other. Okay, so remember, there are 2 electrons, 2 unpaired electrons that sit right up here. So there is a domain that's sitting up here that we can't see. Okay. This domain is repelling the 3 bonding domains and pushing them down. Okay, so what happens in this case is that there are 2 electrons sitting here, okay, sitting right up on top here, right? And they're repelling these 3 bonds. So instead of being planar, it pushes them down into a pyramidal shape. Okay, so they're repelling each other. So they want to be as far apart as possible. Right? And we'll come back to that one. Let's compare that to BF3. Well, in BF3, we have this. Okay, so boron has an incomplete octet, and that's okay, he does that. Right? So in this case, there are 0 non-bonding, and there are 3 bonding for a total of 3 electron domains. All right? So we come to our little chart. We have a total of 3. We have 3 bonding and 0 non-bonding, so that would give me my trigonal planar shape. So we would get this B, F, F, and F. And I want to show you. And it gives us this shape, and it doesn't, I don't have a hole, so it doesn't fit well. So it gives us this. Now I want to compare that to this. I want to compare these two. Why is this one not in the same plane and this one is? Well, if we look at this dot diagram right here, there is no electrons sitting up on top. Okay, so they're not going to be pushed down. They're not going to be repelled. Matter of fact, they don't want to be repelled because if this goes down like this, it forces them actually closer together. So to be as far apart from each other as possible, it forms this planar, okay, this planar shape, right? And this bond angle would be actually 120 degrees. Now, just for fun, let's look at H2O. My question is, why isn't water linear? Well, look at what happens here. If we actually draw the dot diagram, we have 2 non-bonding and we have 2 bonding. Two bonding and 2 non-bonding. If we go to our for a total of 4, if we go to our chart, here's my 4, 2 and 2, it gives me this bent shape. So let's focus in right here. So if we look at our, where is it? I took it apart. If we look at our water molecule, okay, the reason it's not bent, the reason it's bent and not linear is you have to remember that there are 2 more electron domains. Okay. One of them is sitting coming up this way, and one of them is sitting coming up this way. We can't see them because they're unbonded pairs or they're non-bonding pairs, right? So they end up making this, still make this tetrahedral shape. So let's go to our tetrahedral. I built it. So this is where we have 4 bonding domains. Okay, this would be like our methane. This is our tetrahedral shape. If we make this bonding pair a non-bonding pair, so there's still electrons here, all right, we get a trigonal planar. If we take this one off, these electrons are still here, but now we have bent. So you can see how those domains are affecting these different shapes. Okay. So hopefully that helps and you can see it. You're going to actually play with this in the lab some. So let's look at what do I want to look at? I want to look at let's look at some of the crazy ones. So some of the bigger ones. So I want to start with a trigonal bipyramidal, which is our base shape. Okay. And here it is. So this is our AB5. Okay, and this is with this would be 5 bonding domains and 0 non-bonding. Well, what if we take one of these domains away? Okay, what if we take one of these domains away and we have a non-bonding pair here? Well, what this makes is what's called a seesaw. Okay, so there's a bonding domain here that's still pushing these two down, right? But this is called a seesaw shape. Okay. SF4 will make this. Well, what if we take one more of these away? If we take another one away, whoops. Okay. We still have a non-bonding pair here and a non-bonding pair here. All right, so there's still, those non-bonding pairs are still there, but that's how another way we can get a T-shaped. If we take another one away, we can end up with a linear. Okay, now in this case, you still have to remember we have a non-bonding pair here, we have a non-bonding pair here, and we have a non-bonding pair here. So that's how we could get to a linear from a 5-electron domain. Now there's some weird shapes for octahedrals too. So let's go ahead and put an octahedral together. And again, it's the same idea. We're just taking off bonding pairs and making them non-bonding pairs. So here's my octahedral. If we take off one bonding domain, let's take this one off, and make this a non-bonding. This is what's called a square pyramidal. I'll put it this way so you can see it this way. Okay, this is a square pyramidal. Right? There's an electron, non-bonding electron domain here. If we take another one off, this is called square planar. All of them are in the same plane, and we get a square. If we take another one off, that would be T-shaped. If we take another one off, we would be back to linear. So we can get all these shapes just by using VSEPR. All right. Now, the effect of non-bonding electrons on bond angles. So what I wanted to do is I want to start with our tetrahedral. Right? This is our CH4. When we measure this bond angle, all of these bond angles are exactly the same. Okay, they're equally distant from each other. So the bond angle here is 109.5 degrees. So all of these are 109.5. Now, let's compare that to ammonia. All right, so we still have a similar shape. Okay, this time we have a non-bonding pair sitting up here. So you would think that this angle would still be 109.5, but it's not. Right? So it turns out with nitrogen, or ammonia, excuse me, that this angle right here is about 107 degrees. It's less. Okay, so remember this one right here is still 109.5, right? But this is only 107 degrees. If we compare that to water, let's go back to this. If I had one bonding domain, so right now we have 4 bonding domains, sorry, and this angle right here is 109.5. If we take one of the bondings off and put a non-bonding here, this angle decreases to 107. If I take another one off, and now I have 2 non-bonding, this angle, or water, this bent molecule, its angle decreases even more down to 104.5 degrees. It gets even smaller. Now, what is this telling us about this molecule and adding our non-bonding electrons? Well, they're having a greater effect than bonded electrons, and this is why. The non-bonding electrons experience less nuclear attraction because they are only attracted to one nuclei. This allows the electron domain on non-bonding electrons to expand and take up more space. And that will ultimately decrease bond angles. So let's take a look at what's happening up here. Okay, so here all four of these are bonding electron domains. Okay, so they repel each other equally. So we get this equal bond angle of 109.5. In this case, we have one non-bonding, and these two electrons are only attracted to one nucleus. Compared to over here, these two electrons are attracted to two. This allows this domain to get bigger. And if this domain get bigger, it's going to push or repel these down further, and it's going to decrease this angle. In this case, now we have two non-bonding electron domains, and they're bigger than bonding domains, which is going to force this bond angle even closer. All right, let's talk about effects of multiple bonds on bond angles. So the electron domains for multiple bonds, what do I mean by multiple bonds are doubles and triples? Exert a greater repulsive force than single bonds. Now, does that make sense? Well, it should, because think about how many electrons are in a single bond versus a double bond versus a triple bond. Single bond, we only have 2 electrons in that domain. Double bond, we have 4 electrons. It's much more negative. Triple bond, we have 6. It's even much more negative. So if we look at something like this, so in this case, we have 0 bonding or 0 non-bonding and 3 bonding. So if we go to it, this should be trigonal planar. Okay, it should be trigonal planar. So we would think that these would all have 120-degree bond angles. Let me build it for you. Nope. This and this. Here it is. Here's my carbon, my double bonded oxygen, my 2 hydrogens. All right, in a normal trigonal planar, okay, these would all of these angles would be 120 degrees. Well, it turns out, that when you have something like this bond angle is not 120 degrees. Okay. It turns out that this guy down here is about 116.4. And it turns out that this angle is 124.3. So what it's saying is this bonding domain is pushing these two Okay, it's pushing this down a little bit. Okay, so it's having a greater repulsive force than if this was just a single bond. Okay, so our double and triple bonds affect those bond angles. Okay, it affects those bond angles. All right. That's where we're going to stop for today. Okay. I'll make sure that I get something like this posted so you have it. All right. And yes. Okay. We'll be practicing this in the lab. All right. So you're going to have some homework with this, but you're also going to be practicing and looking at this in the lab. All right. So have a good afternoon, and we will see you soon.